Alright, next up we are going to talk about some different properties of liquids, like viscosity, surface tension, and capillary action. Funny story, I looked out the window earlier today and I saw one of our little goats had escaped from his pen, and I went and caught him, put him back in the pen, and before I could turn around he already had his head sticking out of the hole where he had escaped from, so I had to close that up. Anyway, those little goats can escape through anything. So first thing we want to talk about is viscosity. I'm sure you guys have all heard this term. This is resistance to flow. Okay, resistance to flow. We all know, like, if you take water and pour it out and watch it pour out of like a pitcher versus maple syrup, the maple syrup's a little bit more viscous. It's a little thicker. It doesn't pour as easily. And then honey would be even thicker and more difficult to pour. We also have some, you put motor oil in your car, and some of it is multi-grade or multi-viscosity. It changes the viscosity based on temperature, so you don't have to change the oil based on the outdoor temperature. Anyway, generally speaking, higher intermolecular forces give us higher viscosity. There's not much more to say here, but if you have a higher intermolecular force going on in your molecule, you're going to have higher viscosity. A couple fun things are what we call non-Newtonian fluids. I don't always talk about this, but I think it's kind of interesting. You can do this at home. Non-Newtonian fluids are fluids whose viscosity does not behave like we would expect. Okay, normally you warm up something, like you warm up that maple syrup in the morning, pour on your pancakes, it becomes less viscous. So non-Newtonian fluids don't necessarily behave like that. And we have shear thinning and shear thickening fluids. First, let's talk about shear thickening. And really, this is just for general interest. Shear thickening fluids. So what is a shear thickening fluid? When you apply a force, the viscosity goes up. Well, this just means that the viscosity changes with applied force. So I can think of three examples of shear thickening fluids. One is quicksand, and it is real. You won't get sucked down into it your whole body. I've been stuck in quicksand at a lake before when I was fishing by myself. Got stuck up to my knees, and it was very, very difficult to pull out because every time I pulled my leg out, the sand got thick, and then I'd relax and it would get thin again. So you just have to go very, very slow, and you can pull yourself out. I said three examples, I meant two. The other one is a cornstarch and water mixture. Try making this at home, it's kind of fun. Just combine some cornstarch and water, and when you get the right consistency, it's a lot of cornstarch for the water. You can't even stir it, it's so thick. You can actually pick it up, roll it into a ball, and as long as you keep rolling it, it'll stay a ball. You set it down or let it sit in your hand, it just melts into a liquid. Okay, it's really fun to play with. My kids love it. They call it non-Newtonian ooze. So you can just Google that, non-Newtonian ooze, if you want to. And there's also shear. I'm not sure if I'm spelling shear right. It doesn't matter. Shear thinning fluids. They're used to me making stupid mistakes. So the viscosity here goes down when they get thinner when you apply a shear force. So one is concrete. If you've ever watched anybody pour concrete, professionals pour concrete, they pour it into the form and they take a big machine that vibrates the concrete and they put this, I'm really trying hard not to say a certain word. They put this thing down into the concrete and it vibrates it and it makes it flow into all the little nooks and crannies. So if you don't do that, it doesn't fill the form correctly and the concrete is not as strong as you would want. But because you apply that shear force in the form of a vibration, the concrete flows more easily and it will completely fill the form. Here's kind of a weird one. I like food. I studied food chemistry. Vegetable purees. Or as my wife calls them, purees. I don't know. She always mispronounces puree. It says puree. Like ketchup or butternut squash soup. So you guys all know that ketchup doesn't really like to flow out of the bottle very well, but if you give it a little tap on the bottle, it comes pouring out. Why? You apply a shear, you change the viscosity. There's a lot of stuff going on there. Obviously, we're not talking about why. Butternut squash soup is the same. If you make a really thick butternut squash soup like I like to do in the winter, it sounds kind of weird, but you can take a spoonful of it and set it on top of your bowl of soup, like kind of pour the soup out very gently, and you'll have a little mound of butternut squash soup on top of your butternut squash soup if it's thick enough. You jiggle the bowl, it just goes away. So that's a shear thinning fluid. Okay, enough goofy stuff. Oh well, chemistry is all pretty goofy. Let's talk about surface tension. I hope that was interesting for you anyway. Surface tension, okay? Let's take a coin. You guys have probably all done this in like junior high or something, elementary school. Excuse me. Start putting drops of water on it, okay? You guys, like I said, you've probably done this. So if you start putting drops of water on it, eventually you get to the point where you get like this big bubble of water, and it looks like you shouldn't be able to keep that water on there. Now, what is going on? Well, at the surface, there is tension. So we have a little molecule right here that is being pulled in that direction, and we have that happening all over, okay? But why is that? Well, let's take a look. Let's kind of zoom in on a water molecule. Let's just pretend we have the surface of the water right here, and here is our, oh, come on. That's a really weird looking circle. There's one water molecule, and then down here in the middle is another molecule, okay? So what's happening at the surface? Well, this water molecule is being pulled by its neighbors, and again, you know, there's water molecules all along in here, okay? This water molecule is being attracted this way, and this way, as well as, you know, pretty much every direction. This water molecule here down in the middle is being attracted in every single direction you can think of. And again, this obviously goes in 3D as well. We're just drawing it in 2 dimensions. But if we look at the net force, all of these arrows for this guy right here, they all cancel out. So there's no net force. Okay, it's pulled in every direction equally. But look at this water molecule up here on the surface. These two cancel out, but notice there is a net downward pull, okay? So that is surface tension. It's just that asymmetrical pull for molecules on the surface, okay? And that's all that causes surface tension. You can have a little, you guys have seen probably spiders or water striders walking on water. That is how they do it. How does it, if you're a fly fisherman or fly fisherwoman, how does the fly float on the water? Surface tension, okay? It's all because of surface tension. Now, one more thing in this video, talk about capillary action. Oh, I didn't mention. Why do we have surface tension? Why do we have that tug? it's because of intermolecular forces. The red arrows here, it's because they're being tugged in opposite directions, or in all directions, by the other molecules, okay, because of intermolecular forces. Capillary action, or also called capillary rise. We all know that if we stick a piece of paper towel into a cup of water, the water will rise up that paper towel due to capillary action. You may have also had your blood drawn, just like a little drop to test, say, your iron level. You take that little tiny glass tube, touch it to the drop, boom, sucks it right up. That's capillary action. So if we have a glass tube, let's see. This is just a very narrow glass tube, also known as a capillary tube. And we put it into some water. What happens is that the glass and the water are attracted to each other. So what happens is the water actually tries to climb up the glass, and we get that meniscus that we're all so familiar with from all of our glassware. And that's because, again, if we look, kind of zoom in here, what's going on, oops, wrong color. If we zoom in and look, the water on the edge right here is attracted to the glass and is trying to climb up the glass, and that's happening in 3 dimensions all the way around. So that means all of the water is being pulled up that very narrow diameter tube. Okay? The opposite will happen if we stick a glass capillary tube into some mercury. So take that same glass capillary tube, put it in the mercury, and we get the exact opposite. We get the exact opposite meniscus, and the water actually is repelled by the glass. I'm sorry, the mercury is repelled by the glass and pushes down, okay? And that's all due to intermolecular forces. There's no intermolecular attraction between the mercury and the glass. Glass and water like each other, so you get that rise. All right, that's enough.